So I want to take a look at r squared when we talk about linear regression. So you recall that when doing linear regression, so fitting a line, or we've already done linear regression with more variables, plane, etc. if we were in higher dimensions, to a set of data. The r squared statistic tells us how well the line or plane or whatever fits. So we know that r squared runs between 0 and 1. If r squared equals 1, we have a perfect fit. And if r squared equals 0, we have no fit at all. Basically, the data can't be explained by something straight. And so we sort of have a range here. The closer you get to 1, the better the fit is. And the closer you get to 0, the worse the fit is. But I want to have a closer look at how you actually compute r squared. So remember, let's say we have m data points. And we will start with just a straight line. So we'll have data points x1, y1, all the way up to xm, ym. We've looked at this before many times. So let's say x1, y1 is right there, maybe x2, y2 is right there, x3, y3, a bunch of data points, and we draw on the line of best fit. According to the least squares process. We know what it is we're trying to accomplish here. So the y value of this first data point is y1. The y value that the line says we should have at that x value, so this is the x value x1, we will call y1 hat. And you know you get y1 hat by plugging x1 into the straight line. And so what we're trying to do, of course, when we find the line of best fit according to the least squares process, is minimize this error, the error in the y value between the actual y value, y1, and the predicted y value, y1 hat. And again, y1 hat, so yi hat is just your slope times your xi plus your b. You just take your x coordinate, plug it into the straight line, you got your slope and your y-intercept, and figure out what i hat is. And so what we're trying to minimize, of course, is the sum of these errors, these vertical errors. We've done this several times. So we're trying to minimize the sum of the errors. So y1 minus y1 hat, that's this distance right here, all squared, plus this distance right here, which is, if this is x2, y2 minus y2 all squared, plus all the way up to ym minus ym hat all squared. And of course we can write this in sigma notation, if we like sigma notation, the sum as I goes from 1 to m, sometimes we don't even write that when we're in statistics class. We just write yi minus yi hat. And it's understood that I goes from 1 to m. We call this RSS. RSS stands for residual sum of squares. These errors, these residuals, we're squaring those and summing them up, so that's not a bad way of writing it down. Residual sum of squares. Now, I want to remind you something about the least squares line. And that is the fact that one point that is always on the least squares line, one point that's always right on the line, has its x-coordinate, the average of all the x-coordinates of the data points. So this, we'll call that x bar, where x bar is just x1 plus x2 plus up to xm all over the number of data points m. And the y-coordinate of that point is going to be, we'll call it y bar, and y bar is just y1 plus y2. We take the actual x and y coordinates, add them all up, and divide by the number of points to get the average. Oops. And x bar, y bar is always right on the line somewhere. That's something that you would have studied in a statistics class. Now, so the y bar, as we said, is just the y value of that point. I want to take a look at another sum. We're going to forget about the line for a second. Just consider the data points that we started with, the data that we were given, and this height, which you can easily get by taking the average of all the heights of those points. So if instead of taking these residuals, we take the distance between each data point and that average height and add those up. So we'll take the height of the first point minus the average height of all the points. And we'll square that. And then we will take the height of the second point and subtract off the average height of all the points. So forget about the line. This has nothing to do with the line right now. And keep going. Oh, we'll square that. And all the way up to ym minus y bar. So of course, in our original, when we were computing RSS, the residual sum of squares, we took y1 and subtracted off the predicted height at that x value, y1 hat. Here, you can see that even though we go y1, y2 up to ym over here, we just keep using y bar, y bar, y bar the whole time. This has nothing to do with the straight line. And we'll square this. Again, we could write this in sigma notation. We could write I goes from 1 to m if you want, or just leave it out if we were in a statistics class. Yi minus y hat. So what we're actually computing are these distances right here. The distances between each point and the average height of all the points. We're taking those, we're squaring them, we're adding them up. This we refer to, so that was RSS. This we refer to as TSS, the total sum of squares. So TSS equals the total sum of squares. Okay? And our R squared statistic, and this is not how you would have studied it probably in a statistics class, but your R squared statistic is 1 minus RSS minus TSS. 1 minus RSS divided by TSS. I don't know if that's what I said the first time. 1 minus RSS divided by TSS. That gives you R squared. So if the line is perfect, if the line goes through all the points perfectly, then RSS is going to be 0. And so this whole thing is going to be 0, which means we have 1 minus 0, you have perfect fit. And if there is no linear relationship at all, then RSS and TSS are going to be about the same. And so you're going to end up with 1 minus, if these are about the same, you have, this is going to be about 1. 1 minus 1 is going to give you 0. And so this is another look at R squared. Now, I want to look at this in one more dimension, because we're going to need to be talking about a lot of dimensions in the next video. So let's say we still have m data points. So m data points. But we have 2 independent variables and, of course, 1 output variable. So these are our 2 input variables, and we have 1 dependent variable. So I will call, let's say our first data point is x11, x12. So the first one tells me it's my first data point, and the 1 and the 2 say this is 1 input variable, this is another input variable, and then y1. Now you might be wondering why I don't use x and y and z. It's because in the next video we're going to have a lot of input variables. We're going to run out of letters, so we'll just use an extra subscript, as confusing as that may be. So here's my first data point. My second data point is going to be x2, 1, second point, first coordinate, second point, second coordinate, third coordinate, output variable, and so on, all the way up to x, m1, x, m2, y, m. So we have m data points all together. So if we were going to graph this, here's my x1 axis, here's my x2 axis, and here is my output axis. So maybe my first data point is at x11 and x12, and is at height y1. So my first data point is right there, and I have a bunch of data points. We've done this already. And we fit, not in this case a line, we fit a plane to this. So I apologize in advance for my bad drawing, but we have some plane which fits those data points, just like we try to fit a line when we have just 1 input variable and 1 output variable. Well, we can compute RSS and TSS exactly the same. So our first data point is up here at height y1. Let's say at that x11 value and x12 value, the plane predicts we're at this height. Then this is what we use to compute the RSS, the residual sum of squares, the distance between the actual height and the predicted height. It is exactly the same expression for RSS that I've cleverly erased, but was certainly in your notes by now, assuming you're taking notes, which I hope you are. And when we compute TSS, what you do is you take the average of all the heights of these points. So you take y1 plus y2 plus y3 all the way up to ym. Again, we're using y as height. And you divide by the total number of points, and that gives you a point on the plane of average height. And you compute when you're using the average height, you go from a data point to the average height and you square that. So you have exactly the same expression for TSS, exactly the same expression for RSS as you have in your notes. And R squared is still 1 minus RSS over TSS. And again, if R squared is equal to 1, the points fall on the plane. The plane fits the points perfectly. If RSS is equal to 0, then no plane can explain the behavior of the data.